Usually when you flip a light switch or when you pull up to the pump to put gas in your car,
Yeah.
there is this expectation of absolute permanence.
Oh,
Like
absolutely.
you turn the key, the engine roars, the house lights up. It just feels very clean. It feels guaranteed.
Right. We take it entirely for granted.
We really do. We like to imagine that the systems keeping our daily lives running are invincible. Just, endless grids of solid steel, concrete, and deep underground pipes that will simply always be there.
It is a very comforting illusion. We naturally assume that something as massive, as globally critical as our energy supply, well, it must be built on a foundation of absolute stability.
Because to think otherwise is terrifying.
Exactly. We crave that certainty because the alternative is deeply unsettling.
But then you actually look at the underlying map of how that power moves around the globe. You trace the literal physical paths of where our fuel comes from, and suddenly that illusion of invincibility just completely shatters.
It really does.
We are looking at a logistical landscape that is, quite honestly, terrifyingly fragile.
It is the absolute definition of a systemic bottleneck. I mean, we rarely ever pause to think about how energy physically travels to us until something breaks.
Right.
And today, we are looking at the ultimate what if something breaks scenario and the massive, radical global redesign that has been proposed to fix it.
That is exactly what we are getting into today. We are pulling you, and by you I mean the listener, sitting right there into a deep dive on a radical strategic concept that aims to completely rethink how power moves across the globe.
It is a huge shift.
It is. We are analyzing a blueprint titled Video One Internet of Energy, and the core mission of this concept, based on the source material we have today, is to outline a proposed shift from a fragile, bottlenecked global energy system to a highly resilient distributed network.
Which forces us to confront the uncomfortable reality of our current infrastructure.
Yeah, it's not pretty.
Not at all. The global energy system, as it operates today, is entirely dependent on a handful of geographical choke points. We have engineered a global economy that requires uninterrupted, massive flow through incredibly narrow, vulnerable spaces.
Okay, let's unpack this because the strategy we are looking at highlights one specific, deeply critical vulnerability. It points directly to the Strait of Hormuz.
Yes, the big one.
Right, we are talking about a geographical reality where roughly 20% of the world's entire oil supply passes through this one very narrow maritime corridor.
20%. It's staggering.
It's insane. Relying on the Strait of Hormuz is essentially like having 20% of the entire world's blood supply flowing through a single, easily pinchable vein.
That is a very visceral way to put it, but accurate.
Well, if the stakes are literally global market shocks, rapidly rising oil prices, and completely wrecked supply chains, why on earth has the global economy tolerated such a massive single point of failure for so long?
If we connect this to the bigger picture, we have to look at the historical, geographical, and frankly, the economic realities that created these bottlenecks in the first place.
Right, it didn't just happen by accident.
Exactly. You have to remember that the Earth's geography dictates where the resources are actually extracted and where the oceans actually allow massive supertankers to travel. The Strait of Hormuz happens to sit right at the exit of the Persian Gulf, where a massive concentration of the world's crude oil is produced.
But, surely we could have built alternatives. I mean, we build massive infrastructure projects all the time.
We do, but for decades, the path of least resistance, and crucially the most cost-effective route, has been to funnel ships through these naturally occurring narrow straits.
Because building around them is too expensive.
Astronomical! Building overland pipelines that cross multiple sovereign borders, traversing mountain ranges and deserts just to bypass a strait, requires massive capital investment and incredibly complex geopolitical treaties.
Oh, wow. So it's just easier to use the water.
Yes. So the market, which always optimizes for short-term efficiency and cost, simply accepted the geological choke point. But the problem is, this framework explicitly redefines this dynamic. It stops looking at the Strait of Hormuz as just a localized maritime shipping issue or even strictly an energy sector problem.
Bigger than that.
Much bigger. It elevates it to a major risk for the entire global economy.
Because the ripple effects are entirely unavoidable. I mean, if a conflict, a political dispute, or even just a massive physical accident blocks that specific route, the consequences hit your wallet almost instantly.
Oh, overnight, oil prices rise rapidly.
Right. And when that happens, the cost of literally everything scales up. It becomes more expensive to manufacture goods in a factory, more expensive to package them in plastic, more expensive to power the container ships carrying them across the ocean.
And more expensive to fuel the diesel trucks delivering them to your local store.
Exactly. The supply chains just snap, leading to global markets experiencing serious compounding economic shocks.
Yeah.
It is a massive domino effect waiting to happen, all because a few miles of water become impassable.
Which is terrifying because the current system is highly centralized by default. It relies on the absolute perfection of uninterrupted flow through these hypercritical arteries.
Perfection is a dangerous thing to rely on.
It is. When you have an entire system built around central nodes of vulnerability, a disruption does not just cause a local delay, it creates a systemic shockwave that propagates outward. You are essentially balancing the entire global economic structure on the edge of a few geographical knife edges.
Which brings us to the core of the proposed solution. This is where the strategy shifts from just identifying the catastrophic risk of a disrupted choke point to outlining what is called the Global Energy Corridor system.
Right, the new paradigm.
And the crucial element that defines this strategy is that it is fundamentally not designed to replace existing routes. It is not about tearing down what we have.
No, not at all.
Instead, its purpose is to connect those existing vulnerable routes into a flexible, distributed energy transportation network to insulate the world against those massive economic shocks.
That distinction, connecting rather than replacing, is a profound shift in how we approach global infrastructure. We are so conditioned to think linearly about logistics, point A to point B.
Here's where it gets really interesting, because you are right. Human instinct in infrastructure is usually just to build a bigger, better version of the thing we already have.
Always.
If a city pipe is clogged, civil engineers dig it up and lay down a wider pipe. If a highway is horribly congested, the government spends billions to build a massive new bypass.
Exactly.
So in the context of global energy, why is simply connecting existing, flawed routes fundamentally safer than just marshaling international resources to build one massive fortified bypass entirely around the Strait of Hormuz?
Because a massive new bypass is still just a single point of failure. It is applying a 20th century mindset to a 21st century problem.
Okay, how so?
Think about the mechanics of a single mega pipeline designed to bypass the strait. If you put all that capital and all that flow into one new alternative route, all you have done is move the bullseye.
Oh, I see.
Right. You have created a brand new target for sabotage, natural disaster, or geopolitical blackmail. The philosophy of a distributed network, which the Global Energy Corridor system is entirely based on, works on a different principle entirely.
By diffusing the risk.
Exactly. By connecting multiple existing routes into a flexible web, you actively diffuse the risk.
But how does the diffusion actually work in practice? I mean, if the main route is blocked, a web doesn't magically create more capacity out of thin air.
No, it creates capacity through agility. A centralized system relies purely on brute strength, a thicker pipe, a wider, deeper shipping channel.
Right.
But a distributed network relies on routing intelligence. If a centralized pipe breaks, the flow completely stops and the pressure builds until the system fails. But in a distributed web, if one major strand breaks, the physical infrastructure is designed so that the flow simply finds another path.
It just goes around.
Yes, the stress is shared across dozens of smaller, interconnected nodes, rather than resting on one massive load-bearing pillar.
It is the difference between relying on a single concrete column to hold up a roof versus building a geodesic dome where the physical stress of the structure is seamlessly distributed across hundreds of intersecting points.
That is a perfect analogy.
And the overarching metaphor used to explain exactly how this agility functions is brilliant. The framework flat out states that this system works exactly like the internet.
Yes, the Internet of Energy.
Right. In the digital world, if a major server farm goes offline or an underwater fiber optic cable is accidentally severed by a ship's anchor, your email doesn't permanently stop. The data is instantly and automatically redirected through another open route.
It routes around the damage.
Exactly. The Global Energy Corridor system applies this exact same logic to the physical transportation of energy. If one route is blocked, the system does not stop, it reroutes.
And the comparison to the internet is incredibly precise when you look at how network protocols actually function. The original architecture of the internet, specifically ARPANET, was designed by researchers precisely to survive partial network destruction during the Cold War.
Right, it was built for survival.
Exactly.
Yeah.
It utilizes packet switching, where a piece of data is broken down, and the network dynamically calculates the most efficient path for each packet to reach its destination, completely bypassing damaged or heavily congested nodes.
Which is incredible for data.
Yes,
And-
and this blueprint is proposing that we take that purely digital logic, that architecture of survival, and superimpose it over the heaviest, most physical, most unwieldy industry on planet Earth.
Okay, I have to push back here. I love the concept, but moving ones and zeros through fiber optic cables at the speed of light is easy. Data is completely weightless,
It has no mass.
right? It has no mass, no friction, no physical footprint. You can't just apply packet switching to millions of barrels of highly combustible liquid. How does that rerouting logic actually hold up when we were talking about moving physical crude oil or natural gas? You know, you can't just hit a digital refresh button and instantly teleport a massive supertanker to a different ocean.
What's fascinating here is you are hitting on the exact friction point that makes the strategy so wildly ambitious. The sheer audacity of applying a digital framework to physical logistics is staggering.
It seems almost impossible.
You are absolutely correct. A physical barrel of oil or a cubic meter of liquefied natural gas is bound by the laws of physics, thermodynamics, and physical space. So when the framework asserts that the system does not stop and that the system reroutes, it is not suggesting magic.
Then what is it suggesting?
It is demanding an almost unimaginably complex level of physical engineering and global coordination.
Right, because how do you actually reroute a pipeline? A pipe goes in one direction.
That is exactly what has to change. To make physical matter behave as fluidly as digital information, the hardware itself has to be redesigned.
Redesigned how?
Take pipelines, for instance. A traditional pipeline requires massive compressor stations that push the liquid or gas in a single direction. To build an Internet of Energy, you have to engineer bidirectional pipelines.
Oh, wow. So they can flow both ways.
Exactly. You need compressor stations capable of reversing the physical flow of millions of gallons of liquid on a dime. You also need massive intentional slack capacity built into the system.
Slack capacity. But isn't that incredibly inefficient? I mean, energy companies are obsessed with running pipelines and ships at 100% capacity to maximize profits. They don't want to build a billion-dollar pipeline just to leave it 30% empty, just in case.
And that is the exact paradigm shift this framework is arguing for. It requires moving away from pure, fragile efficiency toward robust resilience.
So you intentionally underutilize it.
Yes. In this proposed network, you intentionally operate routes slightly below maximum capacity so that if a major artery like the Strait of Hormuz is blocked, the surrounding routes have the physical room to absorb the diverted flow.
That makes sense, but it must be a logistical nightmare to manage.
It means having a sophisticated, real-time global telemetry system where a supertanker halfway across the Pacific can be algorithmically diverted mid-voyage to a different port because a congestion point was detected thousands of miles away.
It is mind-boggling when you actually start breaking down the physical hardware required to make this work. We are not just talking about laying down a few extra pipes.
No, not at all.
The architecture for this multi-route network involves a massive integration of diverse technologies. We're talking about connecting overland pipelines, LNG terminals, massive inland storage facilities, deep-water offshore energy hubs, and coastal export terminals. And the strategy makes a very firm declaration. It says, this is not a single pipeline project. This is a global energy network.
That specific list of infrastructure pipelines, ships, offshore hubs is not random. The text is intentionally highlighting a highly diverse array of technologies and physical transport mediums.
But doesn't that massive variety actually make it harder? I mean, it is like trying to build a seamless computer network. But one node is a Mac, one is a Windows PC, one is a punch card mainframe, and one is just a guy with an abacus.
That is quite the visual.
But it's true. You have gas that needs to be super cooled to minus 260 degrees Fahrenheit just to become a liquid for the LNG terminals.
Yeah.
You have heavy, unrefined crude oil pumping through massive steel pipelines across continents.
And offshore hubs sitting out in the middle of deep ocean water.
Right, and massive storage tanks buried inland. If we are relying on everything from deep-sea offshore hubs to specialized LNG terminals to act as the physical routers of this network, doesn't that require an impossibly complex level of standardization?
It requires a monumental level of standardization, yes, but that diversity of infrastructure is precisely what generates the resilience.
Really? Perhaps so.
Think about the vulnerability of uniformity. If your entire global network relies exclusively on one type of technology, say overland pipelines, then A singular disruption to pipeline technology creates an unmitigated crisis.
Like a cyber attack on the pressure valves or something.
Or a physical break in a main trunk line, exactly. But by mixing pipes, ocean-going ships, specialized cryogenic terminals, and vast physical storage reserves, a failure in one medium can be mechanically covered by another.
Okay, walk me through how that actually works. Like, if a pipeline breaks, how does an LNG ship fix the problem? They're entirely different states of matter.
Okay, let's use a real-world mechanical scenario based on this framework. Imagine a major overland natural gas pipeline crossing a border is suddenly compromised and shut down.
Okay, the pipe is blocked.
The pressure drops, automated safety valves lock the pipe, and the flow of energy to a major region completely stops. In the old centralized system, that region simply goes dark or freezes.
Right.
But in the global energy corridor system, the moment that pipeline shuts down, the network reacts. A digital signal is instantly sent to an offshore energy hub in the ocean.
Okay, so the offshore hub gets the signal. What does it physically do?
That offshore hub might be a floating storage and regasification unit, which is essentially a massive ship that holds liquefied natural gas. The hub is instructed to immediately increase its output.
So it starts pumping.
Yes. It begins taking the supercooled liquid gas, running it through seawater heat exchangers to warm it back up into a gaseous state, and pumping it directly into a different localized pipeline connected to the shore, completely bypassing the broken overland route.
Wow.
At the exact same time, deep inland storage facilities are digitally signaled to release their reserves to maintain the baseline pressure in the local grid.
So the slack capacity in the storage facilities acts as a buffer.
Exactly. And while the local grid is surviving on those storage reserves and the offshore hub, the broader global network is recalculating.
And GPS routing around traffic.
Yes, LNG carrier ships that were originally destined for entirely different continents are diverted mid-ocean to come restock the offshore hub that is now working overtime.
That is incredible.
The energy flow seamlessly shifted from an overland pipe to an offshore liquid terminal to massive storage tanks and involved rerouting ocean freight, all to ensure the end user never experienced a drop in power.
It is physical redundancy on a planetary scale.
Yeah.
It is exactly like having multiple backup hard drives and cloud servers. But instead of server racks in a data center, you have massive physical storage facilities holding millions of barrels of crude.
Yep, it's the exact same principle.
Instead of fiber optic bandwidth, you have bidirectional pipeline capacity. Instead of data packets, you have massive tanker ships acting as mobile energy caches.
And that is why the emphasis on this being a global energy network rather than a single project is so vital to understand. A single project, like a dam or a mega pipeline, has a discrete start and an endpoint. It is static.
Right, it just sits there.
But a network is continuous and dynamic. It implies a living, breathing, logistical ecosystem that is constantly monitoring pressure, constantly balancing supply and demand across oceans, and constantly calculating the safest, most efficient physical route.
Exactly the same way a computer algorithm calculates the best route for an email to avoid a down server.
Precisely.
So, what does this all mean? We have spent the last 15 minutes talking about geographical choke points, maritime bottlenecks in the Middle East, and complex physical infrastructure that mimics digital algorithms.
We've covered a lot of ground.
We have. But let's bring this deep dive back home to you, the listener. Because at first glance, this sounds like an abstract thought experiment for civil engineers, maritime logisticians, and policy wonks.
It can definitely feel that way.
But this proposed shift from a fragile bottleneck to an internet of energy is fundamentally about protecting your daily life.
Exactly. The abstraction only exists until you go to the grocery store or the gas station.
Right. It is about insulating your personal economy. It is about ensuring that your local gas prices don't double overnight because a ship got stuck in a narrow strait thousands of miles away.
It's about protecting the intricate supply chains.
Yes, the ones that deliver the food you eat, the electronics you buy, and the building materials for your community. It is about ensuring that a localized geopolitical disruption doesn't suddenly plunge the entire global market into a cascading economic shock.
This raises an important question. How do we fundamentally value resilience?
Because it's not cheap.
No, it's not. For the last 50 years, the global economy has valued hyper-efficiency and cost-cutting above absolutely everything else. We relied on those single, massive, fragile corridors simply because they were the cheapest option in the short term.
And now the bill is coming due.
Shifting to a global energy corridor system, retrofitting pipelines to be bidirectional, building massive offshore hubs, and intentionally maintaining expensive slack capacity is not going to be simple, and it certainly is not going to be cheap.
I mean, the capital investment required to physically rebuild the global supply chain is almost incomprehensible.
It is massive. But the argument presented here is that it is the ultimate insurance policy for the global economy.
You have to weigh the alternatives.
Right. The cost of building a resilient network is huge, but the cost of a catastrophic failure in our current centralized system is existential. It represents a necessary global investment in stability over fragility.
It really is a massive paradigm shift in how humanity manages power. The idea of an energy web, where physical resources simply flow around damaged just like digital traffic, is a beautiful, highly resilient concept.
It is a remarkable vision for the future.
But I want to leave you with a final, provocative thought to mull over as you go about your day. We love the internet analogy, right? It perfectly explains the agility and the routing.
It fits perfectly.
But we also know the reality of the actual internet. We know that creating a massive, interconnected digital web inevitably gave rise to malicious hackers, complex firewalls, localized outages, and massive corporate gatekeepers who control the bandwidth.
It opened up entirely new vectors of vulnerability that the original architects never anticipated.
Exactly. So if the world actually pulls this off, if we successfully build this incredibly complex, highly integrated physical internet of energy to finally bypass the old geographical choke points, who acts as the firewall,
That is the big unknown.
who actually controls the algorithms that decide where the energy flows, and what happens when a bad actor decides they don't want to blow up a pipeline, but instead they want to hack or throttle the digital routers controlling the physical power of the entire globe.
It's a terrifying possibility.
It is a brave new world of infrastructure, but it brings a whole new world of risk. Keep questioning the hidden systems that power your world. Thanks for joining us on this deep dive.